Convido o Marcos Vinícius Braga Rodrigues Nunes para ser o mediador do painel Estratégia de Avaliação da Exposição Ocupacional.
Senhores, bom dia. Essa segunda parte da manhã, eu tenho a satisfação para que a gente possa abordar agora um painel que é singular e muito importante para a associação, que é a Estratégia de Avaliação das Exposições Ocupacionais. E eu gostaria de fazer uma recapitulação um pouco da história, bem breve. Para a gente poder compreender o caminho percorrido até aqui, é necessário lembrar a primeira referência datada de 1977, que é o Manual do NIOSH, que também é traduzido pela BHO. E esse marco pioneiro estabeleceu as bases para a avaliação das exposições ocupacionais, agentes químicos, dando início a um processo de desenvolvimento e de abordagens múltiplas. Nas décadas seguintes, o campo evoluiu com muitas contribuições importantes. Com a segunda edição do livro de Estratégia, em 1994, que foi publicado pela AIA, que foi um marco. Posteriormente, tivemos pesquisas e regulação francesa de 2009, que abriu novos precedentes estatísticos. Com a publicação do guia britânico-holandês em 2011. E mais recente, nós tivemos a revisão da norma europeia EN 1089 em 2018. A cada uma dessas atualizações, novas perspectivas são incorporadas e culmina na pré-estreia da quinta edição do livro de Estratégia da AIA. Atualmente nós estamos com a quarta. A quinta está para ser publicada. E essa quinta edição, parte das ideias delas já estão contidas no princípio de boas práticas que foram lançados ontem, que estão na mão dos senhores. Então, os princípios de boas práticas é um documento que representa o resultado de uma confluência de esforços americano, especial franco-canadense e europeu, como um todo, e consolida essa abordagem global para a estratégia de avaliação das exposições ocupacionais. E para isso, para entendermos melhor essas inovações, que hoje se aplicam à higiene, nós precisamos refletir sobre as abordagens bayesianas, ferramenta central na proposta de estratégia do NIOSH. Essa abordagem, formulada no século XVIII, propôs uma maneira de calcular a probabilidade a partir de evidências observadas, com sua capacidade de atualizar as probabilidades à medida que novas informações surgem. A estatística bayesiana se consolidou como ferramenta fundamental em áreas como medicina, engenharia e, mais recentemente, na higiene ocupacional. Neste contexto, nós tivemos a gentileza do Dr. Gurumurthy Ramachandran, que nos cedeu uma gravação da proposta para atualização da estratégia do NIOSH, mais de 4 décadas após sua primeira edição. Essa primeira abordagem integrar explicitamente a estatística bayesiana nas decisões sobre exposição, trazendo a abordagem mais precisa e mais moderna.
Gurumurthy Ramachandran, and I am a faculty member at the Johns Hopkins University Bloomberg School of Public Health. Let me share my screen now. The title of my presentation is the proposed update to the NIOSH exposure assessment strategy for airborne contaminants. My co-authors on this presentation are scientists at the National Institute for Occupational Safety and Health, or NIOSH, and I want to acknowledge their very important role in this. I want to first talk a little bit about the existing NIOSH strategy, which dates back to 1977 and its limitations. And I then want to talk about 2 modern exposure assessment strategies and their performance. And I'll talk about how to evaluate performance of strategies. And then I introduce a Bayesian framework for exposure assessment, and then I talk about the proposed new strategy and its performance. So first, let's talk about the NIOSH exposure assessment strategy. So we start at the left-hand side of this slide, and the occupational hygienist first has to answer the question, are there any chemicals being released into the workplace air? And if the answer is no, then we stop. But if the answer is yes, then the occupational hygienist has to address two other questions. And both of these questions are answered in the absence of any measurements whatsoever. The first one is any employee exposed to the chemical at a concentration greater than the action limit? The action limit is a quantity which is defined as 50% of the occupational exposure limit or the permissible exposure limit for this strategy. So this is answered qualitatively in the absence of any measurements. And if the answer is no, then again we stop and then there's nothing further to be done. But if the answer is yes, then another question is asked. The occupational hygienist has to identify the maximum risk employee or the most exposed employee, and once that person is identified, then their exposure is measured. And if the exposure is less than the action limit, which is 50% of the occupational exposure limit, then again we stop the process. But if not, then there are two other scenarios that occur. One is that the hygienist now has to identify all such employees whose exposure is greater than the action limit. And if the exposures are greater than the occupational exposure limit or the PEL, permissible exposure limit, then all kinds of mitigation strategies are implemented, notifying employees, instituting controls, measuring employees at least monthly, and keep on doing it until this condition is no longer met, until the exposures are brought down. If the exposures are between the permissible exposure limit and 50% of that, then the measurements are made every 2 months until there are 2 consecutive measurements that are less than the action limit. And at that point, we stop the process. So I want to focus on 2 parts of this strategy. The first one is, which I mentioned earlier in the previous slide, assessing if any employee has an exposure greater than the action level, and then identifying the maximum risk employee. There have been a number of studies that have shown that these assessments, which are essentially qualitative assessments using the professional judgment of the occupational hygienist, they are not very good. The accuracy of exposure judgments made by occupational hygienists when monitoring data are not available is not very different from random chance, meaning it's just pure luck, pure chance. And a number of papers have illustrated this. And so any strategy that relies on qualitative judgments is bound to be not very good. The second part of this is identifying the maximum risk employee. It also has a number of limitations. So as before, it is determined by just the subjective judgment of the hygienist. It does not focus on similar exposure groups. In the entire strategy, the 1977 strategy, the concept of similar exposure groups does not even come up once. And instead, it focuses on individual workers, such as the maximum risk employee or other employees whose exposures may exceed the action limit. And so if there is significant between worker variability, then identifying one person as the maximum risk employee is almost impossible, and using such a qualitative approach. And so this is the second limitation of this approach. And then finally, the last part of it is if exposures are greater than the action limit, identify and monitor all employees with exposure greater than the action limit. This does not recognize the idea of exposure variability. And there are no statistical calculations involved in this strategy at all. Each measurement that is made is 1 by 1 compared to the action limit. 1 by 1 compared to the occupational exposure limit. And so this is, again, a limitation, a very serious limitation of this strategy. Another limitation was pointed out by Dr. Stephen Rappaport in 1984, so not very long after the strategy was proposed. And this is a figure from this paper where we have the fraction of exposures greater than the occupational exposure limit on the x-axis. And so this is also known as the exceedance fraction for those of you who have heard this term. And then on the y-axis, we have the probability of non-compliance. So in this strategy, the NIOSH strategy, we compare each measurement to the PEL, and if the workplace is in compliance if all the measured exposures, one by one, taken individually, are less than the permissible exposure limit. So if you just took one measurement, n equal to 1, and if the exceedance fraction in the underlying population of workers is at 0.1, 10%, then the probability of non-compliance is also 0.1. The exceedance is 0.2, probability of non-compliance is 0.2 for n equal to 1. But now if we had two measurements that were made, then the first measurement needs to be less than PEL, and the second measurement needs to be less than PEL. Now suddenly, for again the same exceedance fraction of 0.1, if you make two measurements, the probability of non-compliance goes up to almost 17 or 18%. And same thing if you increase the number of, as you increase from n equal to 3, 5, 10, and now we come to 20, we have now a very high exceedance fraction of almost 80%, meaning that somebody who actually made 20 measurements is almost virtually guaranteed to be out of compliance, even though this is a fairly small exceedance fraction of 10%. So there is a disincentive for workers, there is a disincentive for employers to obtain more measurements. I now want to start talking about how we evaluate the performance of a strategy, and two measures have been traditionally used. One is to look at this exceedance fraction, and the second thing is this 95th percentile. So what I'm showing here is a log normal distribution that we also today know describe most occupational exposures. And if the occupational exposure limit in this case is at 3.5 ppm, then the shaded area, the area under the curve above the OEL, is referred to as the exceedance fraction. And the 95th percentile in this case turns out to be at 5, and then there is an uncertainty around that 95th percentile, and the upper confidence limit of the 95th percentile is at around 9.5 ppm. So how do we evaluate a strategy? What we would really like a strategy to do is to identify unacceptable scenarios. So in this table, I'm showing group exposure profiles along the top, and you can have an unacceptable scenario. For example, a very high exceedance fraction or a 95th percentile that exceeds the exposure limit. So you can have unacceptable or acceptable, and then you have your strategy that decides whether the exposure profile is acceptable or unacceptable. And so if you have a group exposure profile that is in reality unacceptable, and your strategy decides that is unacceptable, that is defined as the sensitivity of the exposure assessment strategy. And in this case, it's pretty high at 90%. The converse of that is if you have a group exposure profile that is unacceptable, but your strategy deems it to be acceptable, that is called a false negative, and that is clearly, very, very undesirable. You want this number, the false negative rate, to be as low as possible. And we also have similar things for if a group exposure profile is acceptable, and your strategy deems it to be acceptable. That's called the specificity of the strategy, and then in contrast, we have the false positives. Of these 4 cells, the left 2 cells are more important, because ideally we would like to be able to identify unacceptable scenarios. So that's where the focus of the performance should look at. So how do we get those numbers, the sensitivity and false negatives and so on? So we use it by developing what are called performance curves. And the performance curve is generated by using simulated data with a known distribution and calculating how often a particular decision strategy results in a compliance or non-compliance decision. So in this graph, on the x-axis again, we have the exceedance fraction, fraction of exposures above the OEL. And on the y-axis is the probability that your exposure strategy deems something to be compliant, meaning it's an acceptable scenario. So for example, at a clearly unacceptable exceedance fraction of 0.25, 25%, the strategy, what we would do is we would generate a number of simulations of a particular log normal distribution with a given geometric mean and geometric standard deviation, and run the strategy again and again and again, hundreds or thousands of times, and figure out how many of those thousands of times does the strategy give you an acceptable decision. And in this case, in this graph, this example, you say that it, for a clearly unacceptable situation, this particular sort of imaginary strategy calls it as being acceptable 10% of the time. And similarly, if it's a clearly acceptable scenario with a 5% exceedance fraction, it calls it acceptable almost 97% of the time. So how does the NIOSH strategy perform? So in this, this was evaluated by a gentleman called Tuggle in 1981. So again, very, very early, shortly after the strategy was proposed. He looked at several different values of geometric standard deviations. And I'm going to just look at the most common one, a variable one, a GST of 2. And again, I'm going to look at one point in this to make my point here, which is that for a clearly unacceptable situation of 25% exceedance fraction, for a GST of 2, we find that the probability of compliance decision is almost 50%. So what it's saying is that this strategy, the NIOSH strategy, almost half the time deems a clearly unacceptable situation as being acceptable. So this is the chart, performance chart, and as you can see, it has a sensitivity of 52%, but a false negative rate of 48, almost 50%. The specificity and false positives actually are pretty nice, 95% and 5%, but the false negative basically tells us that this is not a good strategy for identifying unacceptable scenarios. Now we move on to a different strategy, a modern strategy, and I'm going to talk about 2 of them. The first one is the AIHA strategy. And I'm sure many of you are familiar with this. The AIHA strategy first calls for a basic characterization of the workplace, classification of the workers into similar exposure groups, and for each similar exposure group, or SEG, we make an assessment of exposure to decide whether it's acceptable, unacceptable, or uncertain. And on the basis of this decision, we take various actions, whether to impose controls or reassessment or further information gathering. We also and this is an iterative process. We also see that the AIHA strategy calls for classifying the exposures into 4 categories on the basis of where the 95th percentile of the exposure distribution is located. So if you have a category 0, that means it's a very highly controlled scenario, and the 95th percentile is less than 1% of the occupational exposure limit. As we go down to exposure rating 1, 2, 3, and 4, the 95th percentile increases in magnitude and gets closer and closer to the OEL, until finally in category 4, the 95th percentile exceeds the exposure limit. And so there are a couple of, there are a few important advances that the AIHA strategy made. First one is they introduced the idea of similar exposure groups, unlike the NIOSH 1977 strategy. It acknowledges exposure variability, and there is a statistical approach to exposure assessment. It then says, okay, I'm going to look at some upper tail percentile, such as the 95th percentile, and compare that to the exposure limit, and that becomes the basis of my decision making. For those SEGs that are judged to require quantitative measurements, the strategy calls for about 6 to 10 measurements per SEG, and collecting 1 measurement from each worker. So how does this strategy perform? So on the top right, so on the top left is the performance curve of the AIHA strategy. And you can see on the x-axis now, we no longer have the exceedance fraction, but we are looking at how the 95th percentile compares to the exposure limit. So at the ratio of 1, the 95th percentile and the OEL are identical. If the 95th percentile exceeds the exposure limit, these are unacceptable scenarios. If the 95th percentile is less than the exposure limit, then they are acceptable scenarios. And so again, we see that let's take one point in this curve, clearly unacceptable scenario where the ratio of the 95th percentile to the OEL is at 1.5. And we see that the probability that this is deemed to be acceptable is slightly above 10%. So not so bad. And overall, we see that the sensitivity and false negative rates have much improved compared to the 1977 strategy. It has a sensitivity of 88% and a false negative rate of only 12%, which is much less compared to 48% for the 1977 strategy. But if you look at the specificity and false positives, they are actually not so good anymore. But they are of lesser importance than the sensitivity and the false negative rates. The limitations of the AIHA strategy. So there is still a lot of subjectivity in assessing exposures. Not all SEGs are monitored. Some of them are monitored, and the industrial hygienist or the occupational hygienist has to decide which SEGs actually need monitoring. And some SEGs may end up not being monitored at all due to a wrong decision. The second limitation is that there are a number of ways in which exposures can be assessed other than monitoring. And there is no formal way to incorporate inputs from these other sources of information, such as exposure models, physics-based models, structured deterministic models, or statistical models. And thirdly, this strategy does not account for between worker variability, and the observational method of designing SEGs will not capture this, and this could potentially lead to exposure misclassification. I'm going to briefly also talk about one other modern strategy, which is the British-Dutch strategy. I'm not going to talk in too much detail, though, in the interest of time. except to say that unlike the AIHA strategy, this does account for between and within worker variability. So it calls for 3 workers to be monitored maybe once or up to 3 times each. So a total of up to 9 measurements per SEG. The interesting thing, though, is that even though the British Dutch and the AIHA strategies are very dissimilar, their performance characteristics are very, very similar. And they have almost identical numbers here in terms of their sensitivity and false negative rates and specificity and false positive rates. So they are almost identical in their performance. I want to now briefly talk about these methods for assessing exposures without monitoring data. And there have been a number of papers, lots and lots of papers looking at modeling approaches such as physical chemical models, well mixed room, 2-box, 2-zone models, eddy diffusion models. And there are structured deterministic models based on heuristics and checklists that are the second type of model. And then there are statistical models such as Staffen Manager, which is widely used in the European Union. But there's no clear way of incorporating the inputs or the assessments of exposure from these approaches into the AIHA strategy. Before I get into what we are proposing, I need to tell one more thing, which is that a few years ago there was an innovation made for not only adapting the AIHA strategy, which calls for assessing the 95th percentile relative to the occupational exposure limit, but also providing some measure of uncertainty in the estimate of the 95th percentile. So what do I mean by that? So in this chart on the right-hand side, we are basically saying that the 95th percentile is in one of these 5 categories, but there is a 51.3% probability that it's in category 4, 40% that it's in category 3, 8.7% it's in category 2, and a very small percentage is in category 0 and 1. And so now this is called a decision chart, and it'll play an important role in the rest of my presentation. So now I can talk about the Bayesian framework. So a Bayesian framework provides a way in which we can, in a very transparent and quantitative way, incorporate information from qualitative or modeling approaches that I briefly talked about, and monitoring data. So if you look at so I have 3 columns of charts here. If you look at the leftmost column, in the top left, you have what is called the prior decision chart or prior probability chart. And here, each of the 5 values here represent the 5 categories of the AIHA exposure limit. We are basically saying in this chart that we don't know where the 95th percentile is, which category it's in. It could be in any one of these 5 categories, and they're equally likely, 20% probability. But then I go and make a small number of measurements, 3 measurements in this case, and these measurements now indicate, just on the measurements alone, that the 95th percentile is in category 2, with smaller probabilities in category 3 and 4. And what the Bayesian formula does is it synthesizes the prior probability along with the likelihood, which is in the middle, to provide what is called the posterior probability distribution, which is, in this case, it turns out to be identical to what the measurements are suggesting, because the prior provides no information whatsoever. It's a uniform prior. But now let's look at the middle column. So here, let's say we had used some kind of model, a physics-based model or Staffen Manager or the structured deterministic model. And that suggests, without looking at any monitoring data, that the exposure 95th percentile is most likely in category 2 with a 60% probability. Now we have the same information from the monitoring data, that the category 2 has 65% probability of containing the 95th percentile. And now the Bayesian posterior, which is a synthesis of the prior and the likelihood, is predicting that there is a 90.7% probability that it's a category 2 exposure. So this is sort of if Bayesian statistics works really well and we have modeling input, then this works great. But if we don't have modeling information and the industrial hygienist sort of picks some category at random, in this case category 4, and it doesn't agree with what the monitoring data are suggesting, then you are left with some kind of mess here. And so what we recommend is that we not use the occupational hygienist's professional judgment. We should use monitoring data and actual models. So what is our proposed strategy? The flow chart on this right-hand side, the lettering is a little small, I apologize for that. But this is a synthesis of the AIHA and British Dutch strategies. So we start off by using a physical model or an SDM and create an informative Bayesian prior. And so no measurements have been made at this point. And so if these suggest that it's a category, the Bayesian prior suggests that it's a category 0, then we stop. Then we say, okay, this is an acceptable situation and we should do just routine reassessment after some time. But if it's not category 0, then we start making measurements. And we say, okay, I'm going to make 3 measurements on 3 different workers. And I look at the 3 measurements, if any one of them are above the exposure limit, then we know that it's going to be an unacceptable scenario and we need to implement control measures. But if none of the measurements are below, or none of the measurements are greater than the exposure limit, then we develop a Bayesian posterior and we ask the question, is category 0 or 1 most likely? If the answer is yes, then you stop. If the answer is no, then you collect 3 more measurements and you again go through the same routine. Are any of the measurements greater than the exposure limit? If yes, then you say it's unacceptable. If no, then you develop the Bayesian posterior and then you ask, is category 0, 1, or 2 most likely? The answer is yes, then you stop. The answer is no, then you collect 3 more measurements. So now at this point you have 9 measurements. You develop a posterior and ask, is it category 0, 1, 2, or 3? If yes, then you stop. If no, then it's an unacceptable scenario. The strategy incorporates both AIHA strategy's features of having exposures in 5 categories, but also this thing of progressively increasing the number of measurements. How does this strategy perform? So this is a busy slide, and on the right-hand side, I'm showing the performance curves for several different scenarios. The solid curve is for when you have a uniform prior, and I'm showing the performance chart here. It has a sensitivity of 92% and a false negative of 88%. So this is much better than the AIHA or the British Dutch strategy, and also of course certainly better than the NIOSH 1977 strategy. It's also better in terms of the specificity and false positive probability. So if you do nothing, and even if you don't use models, you just use a uniform prior, and you follow this strategy, you are going to be qualitatively and quantitatively better than any of the existing strategies. What happens if you do actually use an informative prior? So we have category 1, 2, 3, or 4 being identified correctly using models. Then actually the performance improves even further. Now you have a false negative rate of less than 2% and a false positive rate of less than 1%. So it's a amazingly really good performance if we use informative priors. So I want to stop here and summarize what I've presented. The proposed strategy builds on 2 of the current best performing strategies, the AIHA and the British Dutch strategies. It incorporates the use of assessments created using means other than monitoring. For example, physical models, heuristics, and historical data trends. The Bayesian statistical framework can combine the checklist heuristics, physical exposure models, and historical data with current monitoring data in a rational and transparent manner. The performance of this strategy is quantifiably superior to both the AIHA and British Dutch strategies. It becomes even better when accurate priors are used. And finally, the proposed strategy provides an incentive for increasing the sample size, unlike the current strategy where there is a disincentive to getting more than one measurement. So in conclusion, the NIOSH strategy is outdated and does not perform well. And it's important for the premier Federal Occupational Research Institute to develop, adopt, and recommend a strategy to enforcement agencies such as OSHA that is consistent with the best science and practice. Thank you very much.